Alright, good evening, guys. Hello, guys. How are you? Alright, today I am trying to use a different board. You can actually see. I hope it's not gonna disturb. I see my light is visible here. I hope that's not gonna disturb much. I hope you had a wonderful day, a wonderful Friday. We meet again doing mathematics. And guys, today we're gonna continue with our Euclidean geometry. We continue from where we left. Okay, so guys, I want us to just discuss, to have rather what we call a reflection of what we did yesterday. Yesterday we didn't look at much. We only looked at angle and line relationships. We also looked at triangles. Then we looked at parallel lines. Then we went into questions, trying to solve questions and see how we could solve them. Okay, I tried to get a bigger board, guys, so that at least we can have our stuff there, calculating without any problems. Let me try just to shift my table to the other side. Oh, now the setup is gone wrong. I wanted to shift that light away from the board so that guys could see better. Right, I hope this is not gonna disturb us that much. I don't have much of space there, but I hope it's visible. Okay, so we are still looking at Euclidean geometry. Okay, so yesterday we said Euclidean geometry, it actually has 3 sections. Okay, the first one is to do with a line and angle relationships, including triangles. Then the second one is to do with number 2, it's circle geometry. Okay, so today we are going to focus on circle geometry, particularly looking at the theorems of circle geometry. Okay, so guys, I hope you see my body. Maybe it's a new board. I hope you see everything there. Okay, if you don't see, please feel free to say we actually don't see. Okay, so we are going to be looking at circle geometry. We are going to be looking at circle geometry today. Okay, so now let's first look at the circle itself. Okay, a circle is in this way. We know a circle, but we need to know the properties of a circle. Okay, the first thing that we have on a circle, we talked about this when we're talking about curves. We have what we call a tangent. We have what we call a tangent. A tangent is a line that touches a circle at one point. So it actually says hello and later goodbye. Okay, then we have a chord. Right? A chord is a line that actually runs from one side of a circumference to the other side. So this one, it's a chord. Then we have a special type of a chord which is known as the diameter. Right? The diameter passes through the center like that. The diameter. Then we have what we call the radius. Okay, you have the radius. Okay, if we look at the radius there, the radius is actually half of the diameter, because if we look at the diameter, we have a radius there, we have a radius there, then this one is also the radius. Okay, a radius is very important. It is a line that runs from the center to the circumference. Then a diameter, it is a chord. It is a special type of a chord that runs from one side of the circumference to the other side of the circumference, passing through the center. Okay, that is a circle. Okay, right. Then if we look at the chord, guys, I'm gonna draw another circle. I hope it's visible there. Right. If we look at the chord divides the circle into two, right, segments. Right. So we have the major segment. I'm gonna write seg. Then we have the minor seg. So the minor seg is the small segment. Then there we have the major segment, which is the bigger segment. Right. Also, a chord divides our circle into two arcs. You have the minor arc. I'm going to trace the minor arc. The minor arc. And also the other side, we have what we call the major arc, which is in blue there. Okay. So it is very important to know these properties, guys. Okay. So tangent only touches at one. Chord, diameter. Diameter is 2 times radius. Then radius there. And it is also very important to know that the radii of a circle are equal. Just like the spokes of a bicycle. The radii of a circle are equal. Okay. So I am going to try and summarize the theorems. Right. We are not going to prove today, because if we want to prove, it's going to take time. Theorems. Okay. So I'm going to try and summarize the theorems. The first statement is the theorem. Then the next one is what it does. Okay. First part is the theorem, and the second part is what it does. Okay. So number one, it's not in order actually. So it says a line drawn from center of circle. Let me just write center. Perpendicular to chord. Now we know what the chord is. Perpendicular meaning to say it means the chord at 90 degrees. What does it do? So the one that I write in red is what it does. So here it says it.
What is that? The effect of light on your board. I don't know. There's a light on your board. It makes my eyes.
Which is around this side.
Yeah.
Oh my God! And today I changed the room I'm working in. Oh.
Okay. But if there's no way to remove it,
if I do like that, how is it?
Yes.
If I do like
it's
this?
better. It's better.
Okay. Okay. So a line drawn from the center of a circle, perpendicular to chord, it bisects the chord. It bisects the chord. Okay. So we have the theorem statement, then we have what it does. Okay. So now I'm going to draw a circle to show you. Right. I draw the circle there. Then I draw a chord, which is called AB. Then we have a line that is drawn perpendicular to chord. So center, usually we call it center O. Okay. So if you are given this situation, what do we know? This is a line that is drawn from the center, and it is perpendicular to the chord, or to a chord. Right. What does it do? It bisects the chord. So if this one is M, it tells us that AM is equals to BM. Because to bisect is to divide into two equal parts. So what is the reason here? The reason will be line from center perpendicular to chord. Like that. Is it visible, guys? Is it visible?
Yes.
All right. So it means AM is equals to BM. Once you see that we have a line that is from center to the chord, it can pass through the chord to the circumference or pass and go outside the circle. But as long as it is from the center and it is perpendicular to the chord, then know that this line, it bisects the chord. So this one, it has a proof, but we are not going to do the proof, because if you start doing the proofs now, the whole lesson is going to end while we are doing what? Proofs. Okay? We move on. I hope I'm going to move at the speed that is required. So the reason there is line from center perpendicular
So
to
it's
sorry? Hello?
sometimes we can't see very well, sometimes it's coming late, but now it's okay. Now it's playing again.
What's happening with my camera today? It's actually my camera. Let me see. From my side, it's actually see. Is it okay? I heard the voices for Jackie. Is it okay now?
Yeah, yes.
Yes.
Now it's okay.
All right. Okay. Right. Okay. So I'm gonna rub. Now we look at the second one, which is the converse of this one, which is the opposite of this one. I'd rather say, but we'll call it the converse, which says the line from center to midpoint of chord. Right? Line from center to the midpoint of chord. What does it do? It is, now this is the reverse, ne? You see? Now this is the reverse. Line from center to midpoint of chord. What does it do? It is perpendicular to the chord. The line from center to midpoint of chord. What does it do? It is perpendicular to the chord. Okay? So what do we mean by that? What we mean is that we have a chord that is drawn. I want to call it A, B. Then we have a line that is from center there, and we are told that these two sides are equal. What does it mean? It means M is the midpoint of A, B. So this line that is drawn there from the center to the midpoint, it is perpendicular to the chord. Therefore, we conclude to say the angle OMA is equals to 90 degrees. And what is the reason? The reason is line from center to midpoint. Line from center to midpoint. What does it do? It is perpendicular to the chord. Perpendicular, it means they meet at 90 degrees. Perpendicular means they meet at 90 degrees. Okay? So that is the first two. Those are the first two, and we can actually use them. Okay? Right? Then I'm gonna try and be as fast as possible. Right? Then the other one says The angles at center, that is number 2. The angle at center is 2 times angles at circumference. At the circumference subtended by the, when they are subtended by same chord. The angles at center is 2 times angle at the circumference when they are subtended by the same chord. Okay, what do we mean by that? Okay, we have the center there, we have, okay, we do not have the chord there, but we see that a chord can be drawn there. That is actually supporting this one at center. Then there's also this one at circumference. Okay, so if I can name these angles to be A, B, C, then this one is O. What does it mean? It means that A, O, okay, this one is C, A, O, C is equals to 2 times A, B, C. Okay, so this one is twice that one. This one is twice that one. This one needs the proof, but the proof we are going to do it later, not today. Okay, so the reason here will be angle at center is equals to 2 times angle at circum. Because if you try to write it, the whole of it, you are going to fill the whole page. So it's angles at center is equals to 2 times angle at circumference. Okay, so it means B there is half of O there is twice of B. Okay, that is angles at center is equals to 2 times angles at the circumference when they are subtended by the same chord. Okay, the one that actually comes after this one, which is number 3, we talk about number 3. We talk about angles subtended by the diameter. Right. Okay. They are also called angles in the semi segment. Semi means a half segment, the other half of the circle. Okay. So what happens to the angles subtended by the diameter? They are equal to 90 degrees. Okay, so where does that come from? It comes from the angles at center are equals to 2 times angle at the circumference when subtended by the same chord or by the same arc. So it tells us that this one is 90 degrees. Why? Because we'll see that at the center there, this one is 180. So it means that is half of 180, which is 90 degrees. So that is A, B, C, and this one is O. AOC is 180, therefore ABC is 90 degrees. The angles subtended by the diameter equals to 90 degrees. So I can write A, B, C is equals to 90 degrees. So I can say angle subtended by diameter. Okay, or I can write to say angles in semi segment. Many people, they confuse same segment and semi segment. Semi segment means half circle and also half circle. So the angles that are in half circle, they are 90 degrees. Those are the angles subtended by the diameter. Okay, so we move on. We go to the next one. The next one actually, which comes from the number 2 that we talked about there. One that comes from number 2 that we talked about, okay, is number 4, which is angles subtended by same chord on the circumference are equal. Angles subtended by the same chord on the circumference are equal. Okay, so this one is also called angles in the angles in the same segment. What do we mean by that? Okay, if we are having a chord or by the same arc, this is an arc from here to there, subtending two angles like that. Okay, then we have angle A, angle B, C, D. Here you can say this is E. What does it mean? It means we can see that there are many angles that are subtended by the same chord. If I could draw the chord, I could draw it here. Okay, so supporting. You see that one goes there, that one goes there. So it means this angle here and that angle are equal. And if we come down, there's another chord there at the back, which is that one. See that one and that one are equal. They are supported by the same what? By the same chord there. So we can conclude to say, right, angle A there is equals to angle C, and also angle B is equals to angle D. There are two reasons that we can use there. We can say angles in the same segment or in the same seg, just like that. Angles in the same segment, or you can say angles subtended by the same chord or angles subtended by the same arc. It's still the same, it's still acceptable. So angles subtended by same chord, they are equal. Okay, so we saw the chord that I drew up in red, that one, B, D is the chord, but it won't be there. Then also A, C is a chord subtending B and D. Okay, so guys, this is the other one, which is the fourth one, angle subtended by the same chord. Okay, then another one, guys, that we can actually get from there is not from this one. This one is now a bit independent, right? Is the one that talks about okay, it's actually coming from there. Says equal chords subtends equal angles. Okay, what do we mean by that? We have a circle like that, then we have a chord which is subtending angles on the circumference. Then we have another chord here that is subtending another angle in the circumference. If I'm told that this chord and this chord are equal, what does it mean? It means that this angle here and that angle here are equal. So let me just name them A, B, C, then D, E, F. So what does it mean? It means angle B there is equals to angle F. Why? We say equal chords, equal angles. Equal chords subtends equal angles on the circumference. If we are having the same what? Same within the same circle, right? Also, equal chords subtend equal angles at the center. It is also very important for you to know that. Equal chords subtend equal angles at the center. It is also very important. Okay, what do we mean by that, guys? You're gonna see on the video, because now I'm trying to cover my time. Okay, what we mean by that is that if we are having a circle, then we are having a chord that is subtending an angle at the center, right, like that. I told that this chord and this chord are equal. Then this is O1, O2. Then A, B, C, D. It means angle O1 is equals to angle O2. Then again, equal chords, equal angles. Equal chords, equal angles, like that. Okay, so it is also very important to note that they can subtend, the angles can be on the center or the angles can be on the circumference. Okay, that is equal chords, equal angles. Right, we are moving, guys. If I've left anything, I'm gonna review and check if I've left anything, but I think for now we are covered this side. Let's go to the cyclic quad. Cyclic quad, we actually have how many problems, how many proofs or theorems give? I think 2 major. Okay, what is a cyclic quad? What is a cyclic quad? A cyclic quad, it is a quadrilateral. A quadrilateral is a 4-sided shape. Okay, so a cyclic quad, it's a quadrilateral with all 4 vertices actually touching the circumference, like that. Okay, like that. So A, B, C, D. So it means the shape that is inside there, which is A, B, C, D, it's a cyclic quad. So if you see a cyclic quad, just know that there are 2 theorems that you can actually use in solving Euclidean geometry problems. Okay, number 1, it says the opposite angles of cyclic quad are supplementary. Right. When you say supplementary, it means they add up to 180. They add up to 180. So what it means is that the opposite angles here in the cyclic quad are angle A plus angle C is equals to 180. And also the other opposite, the pair of opposite, it's B plus D is equals to 180 degrees. Then what is the reason? Opposite angles of cyclic quad. They add up to 180 degrees. Okay? That is the first one. The opposite angles of a cyclic quad add up to 180 degrees. So opposite angles of a cyclic quad are supplementary, meaning to say they add up to 180 degrees. Okay? Now, number two. Number two says the exterior angle of cyclic quad is equal to interior opposite angle. The exterior and outside angle. If I can extend this one such that we have C1 and C2. If we check, C2 is outside. So that is an exterior angle. So it means angle C2 is equals to angle A, because the opposite of C is A. So the interior opposite. This is outside the quadrilateral. Okay? Then that the reason is exterior angle of cyclic quad. Okay? So we have two major. One, opposite angles of a cyclic quad, they're supplementary. Two, exterior angle of a cyclic quad is equals to the interior opposite angle. That is the second one. Of course, we have proving the cyclic quad. Today, we are not going to look at proofs. I don't want us to look at proving. I just want us to be able to use the theorems that we are talking about. Guys, I've been talking alone for the past 20 or so minutes. Are we there?
Yes.
Okay. Yeah. So I'm trying to cover as much as possible so that you can remember, guys. Then after which I'm going to embark into questions and using this stuff. Okay? Right? Then, when the lesson was starting, we talked about tangents. Okay? So tangents, they have about 3 or so theorems that come. Guys, are we connected? Hi, guys, are we connected?
Yes, but you are breaking, sir.
Okay, I think it's my network here. Can you hear me now?
Very clear, sir.
Okay, thank you. Right, now let's talk about tangents. Tangents. Right? When I was beginning the lesson, I talked about tangent. A tangent is a straight line that actually touches the circle outside at one point. Okay? That is a tangent. So the first theorem that we talk about there is tan chord theorem, which says the angle, I'm going to be patient writing this because this is important, the angle between a tangent and a chord is the angle that is formed between a tangent and a chord is equal to the angle subtended maybe it's supported by the chord in the alternate segment. So they use a lot of jargon here. I will try to simplify. This means the angle between a tangent and a chord is equals to the angle supported by the chord in the opposite segment. Okay? Right. Let me draw a circle. Drawing a circle, I am going to start by drawing. Let me draw a tangent because that's the one that is a bit difficult to draw. Okay? There's my tangent. Okay? Then, there where the circle meets the tangent, if we have a chord like that, the chord divides the circle into two segments, the minor segment and the major segment, if you can remember when I introduced the lesson, right? So we have an angle that is formed here. That one, you can see it, okay? So that angle that is formed between a tangent and a chord is equals to the angle that is subtended, that is supported by that chord where in the other segment. Because this is the minor segment, then this is the major segment. Okay? So if I could name it T, P, Q. Okay? Then we have P1, that angle, P2, P3. Okay? Then we have M, N. All right? So we have two angles, we have two chords there that are actually forming angles with the what? With the tangent. So I am going to draw it this way. I'm going to rub so that I can write the angles that are equal there. Right? I've been talking alone, guys, for quite some time. Can you please tell me which angle is equals to P1? P1 is equals to which angle?
M.
Is it N?
M.
Is what? Is equals to
M.
angle?
M.
M. Yes. Because remember that P1 is formed by this chord and by the tangent. So you check which angle is supported by the chord. It is angle what? M. Okay? So which other two angles are equal there? Which other two angles are equal?
I don't know.
How about P3 is equals to?
It's equal to 3. I mean N.
N.
It's equals to N. And the reason is what? Tan chord.
Tan chord.
Yes, that's the reason. It's equals to tan chord. Guys, I just wanna take off my what do you call it? My Wi-Fi there. I think the Wi-Fi it's actually disturbing my lesson. So bear with me.